We're now on our way of developing this analog of the Fourier inversion theorem for these locally compact abelian groups. And there's one more technical thing we need to develop before we go into that direction. This is called the positive definite functions. It's a very important concept in not only in these analysis on groups, but later on, if you study the C-star algebra or the operator algebra on groups, they play a really important role on basically the states on the C-star algebra. So now we just want to introduce this notion a little bit more, and let's do some basic definition first. All right, so here let's give the definition. So a positive definite function essentially is just a function, let's say phi from G to the complex. I'm assuming G is locally compact abelian in this chapter, so feel free to say it's abelian. But in general, you do have the same notion even when G is non-abelian, okay? So just let you know. So we say this function is called a positive definite. So positive definite. If the following thing happens, so first of all, I have for every G1 up to Gn inside G, I can consider a n by n matrix. So I evaluate phi, the ijth entry, I put the Gi inverse, and then I put a Gj. Okay, I evaluate at that point, okay, for the ij entry, so I get an n by n matrix. So this is inside n by n matrix. And for n by n matrix, then I can talk about its positive definite. So as long as this matrix is positive definite matrix inside this n by n matrix. So positive definite, essentially, well, there are many meanings. So for example, you can say all its eigenvalue are non-negative, or equivalently, what you can say is the following. So equivalently, one way of saying something is positive definite is basically if you evaluate against a vector and then inner product with the same vector or the conjugate, you get something non-negative. So equivalently, you can say for every C1 up to Cn inside the complex number, then the double summation of over I and j of your phi of G I inverse Gj, and you multiply the Ci, and then you multiply the Cj bar, you have something positive, okay? So this is essentially coming from this evaluation. So you consider your matrix, it's an n by n matrix, so you evaluate against a vector, n by one vector, and then you take the inner product against the Cn, okay? So you do that inner product, that's going to be greater than or equal to 0. All right, so of course, all of these are basically equivalent from linear algebra. All right, so here's the definition of positive definite. And well, because we're on a topological group, there's no reason to believe this phi is a continuous function. So let me just add inside the requirement that phi has to be continuous for the positive definite function, okay? So without the continuity, then things can get really messy, okay? For example, you just take the real and you can just assemble a bunch of these kind of positive definite function without worrying about continuity. And in fact, you don't even need to worry about measurability. And that's going to be problematic because we're going to integrate these functions a lot. So let's pretend all the positive definite function has to be continuous, okay? So this is our definition. So for positive definite function, they have a really nice property. So here is a bunch of lemma. So let's assume that phi is positive definite. So sometimes I just use PD, so positive definite. Then first of all, this phi has to be Hermitian. So it's Hermitian. What I mean by Hermitian is that if I evaluate phi at x inverse, well, that's essentially phi of x, but the whole thing takes inverse, okay? Or you can equivalently, you can say phi x is just phi x inverse, the whole thing inverse, okay? They're equivalent. All right, and second of all, in fact, whenever you have something positive definite, then phi has to be inside an L infinity of G, okay? It's bounded. And what did I mean by bounded? Well, it's actually, we can actually compute its infinite norm is essentially just phi evaluate at the identity. Okay, so its infinity norm is given by phi of E. All right, so the proof is really simple. So first of all, if you take G1 is equal to the identity, if you take G2 is equal to X, you consider what is this GI inverse GJ, you can write it out. Well, this is no other than the phi of identity on the diagonal. Okay, you have phi of identity, and then here you have phi x, and here you have phi of x inverse. And you know this is going to be a positive definite matrix, and just from linear algebra, you know if you have a 2x2 matrix, complex value matrix, if it's positive definite, then it has to be a Hermitian matrix. Okay, so the matrix is Hermitian. So by Hermitian, this basically is equals to its conjugate transpose. So immediately you have that phi is Hermitian. Okay, so phi x bar is just phi of x inverse. Okay, they have to be the same. And moreover, if you recall, if a matrix is positive definite, then you have to satisfy few things. So first of all, because now you only have a 2x2 matrix, things are a lot easier. For 2x2 matrix, if you want your matrix to be positive definite, then all the determinant of these diagonal submatrix has to have positive determinant. Of course, you don't have 2x2, so essentially just saying this phi of E has to be positive, first of all. So phi of E, that has to be positive. And also its determinant has to be positive. And what's the determinant? Is just equals to, well, you have phi of E, the whole thing squared, and you minus the phi of x times the phi of x inverse. And you just prove the phi of x inverse is the conjugate of phi of x. So this is just equals to the phi of E squared minus the phi of x, the norm squared, all right? So this is going to be greater than or equal to 0. So in other words, your phi of x squared, or let's just take the square root, is going to be less than or equals to phi of E. And you may already notice phi of E, because, well, first of all, it's on the diagonal, so it has to be real valued, and it's non-negative, so you take the square root, you have this phi of E. So all the phi of x, the absolute value of phi of x is bounded above by the value of phi at the identity. And in particular, phi of E achieves phi of E, of course. So you're in your sup norm, the phi of the sup norm. Okay, so that's going to be less than or equal to phi of E. And of course, it's less than or equals to the sup norm. So all of these are equality. Okay, so let's finish the second part of the lemma. All right, so essentially what we proved is that if you have a positive definite function, then it has to be in the L infinity. All right, so you probably also can notice another thing is that when you scale a positive definite function, let's say by some scalar multiple, well, then of course, it's still, when you scale a positive definite matrix, you still have a positive definite matrix as long as you scale it by a positive scalar. So you can scale all your positive definite function by positive scalars, and you still get positive definite. Okay, that's kind of easy observation. I'm not going to even write it down. The next lemma is going to be slightly technical, so bear with me a little bit. So here's a lemma. We actually want to show that these phi of x is going to be nice enough that they have to be uniform continuous if you have some continuity at one point. Okay, so they're not only just continuous, but they're actually going to be uniformly continuous. All right, so here is a little lemma we need. So if you have phi, let's say it's positive definite, all right, then for every x and y inside your G, then you can evaluate phi x minus phi y. So we want to do the uniform continuity eventually, so that's why we need this difference. Okay, so it's going to be bounded above by the following. It's going to be bounded above by twice the phi of the identity multiplied by the real part of the phi of the minus of phi of xy inverse. Okay, so just without proving it, so as a consequence of this lemma, as you can see, if x and y are going to be really close together, then xy inverse is close enough to E. So because your phi is continuous, the right-hand side is going to be, well, close to 0 because phi of E is going to be fixed. So your phi of X and phi of Y are going to be close as long as your XY inverse is close enough. So that basically is corresponds to phi being uniform continuous. So let me just write it down. So as a corollary of this lemma, phi is actually just going to be uniform continuous, okay? So of course, this is given our definition of positive definite required to be continuity. I know some authors don't require it, okay? So as long as we require the continuity, they're automatically uniform continuous. All right, so now let's prove the lemma. So proof of the lemma. So to prove this lemma, well, you probably already noticed we have an X, we have a Y, and then we have identity. So you probably want to look at a 3x3 matrix being positive definite. Okay, so let's let G1 equals to the identity, G2 is equal to X, and then G3 is equal to Y. All right, so your matrix, this phi of GI, GJ inverse, that's going to be equal to the following. I should say GI inverse, probably. All right. So this one is just going to be equal to the following. So you always have phi of E on your diagonal. Okay, that's kind of trivial. But on here you have a phi of X, and you have a phi of Y. And on here you have your phi of X inverse of Y, or let's say X inverse of Y. All right. And on the other side, you have a phi of X inverse, phi of Y inverse, and then you have a phi of X Y inverse. Okay. Things are technically abelian, so I don't really need to care too much about whether I put the X inverse on the left or on the right. Okay. So our group are always abelian. So now this 3x3 matrix is positive. So now let's think about what we can do. So to use this positive, well, one thing is that I use the formula that basically if I take any three-dimensional vector, I multiply that vector, take the inner product with itself, then I have something non-negative. And because you want to have something like a phi x minus phi y, the absolute value, so you can try to basically pick your vector in a certain way that makes this phi x minus phi y. Well, so this is slightly technical. So in the end, you got to pick C1 is equal to 1, and you pick C2 being some lambda times the phi x minus phi y, and then the whole thing over phi x minus phi y. Okay, so in this way, you got to cancel the x minus y. And then you do the C3 minus equals to minus C2. Okay, so here lambda is a real value. Okay. So now you do because by the positive definite, so we have that the double summation over ij of the phi of the GI inverse GJ, CI CJ conjugate, that's going to be positive. But now you can expand it, okay? So I will just write out the formula. You can try it on your own if you wish. All right, so first of all, if you look at the identity term, it basically got multiplied by all the CI conjugate, okay? The identity only appears on the diagonal. So what you have is 1 as your C1 squared, and then you have the C2 squared and the C3 squared, let's just say, because C3 is negative C2, so you have twice the C2 absolute value squared. And you also have plus a bunch of the phi x minus phi y term and its conjugate. So you have a C2 times phi x minus phi y. And you also have a C2 conjugate. Okay, so you have a conjugate of the phi x inverse minus phi y inverse. But that's just essentially phi x minus phi y, the whole thing conjugate. And by the way of the choice of your C2, you may notice the phi x minus phi y got cancelled, so you end up with something like phi x minus phi y absolute value. Okay, we're going to expand it later on. And finally, for the term of the phi of xy inverse and x inverse of y, what you got to multiply is one copy of the CI and one copy of its conjugate. So in the end, you will end up with actually C, let's just use C2, the whole thing conjugate squared. And one thing you may notice is that when you compute the C2 while you're basically doing the lambda times some vector, the norm of that vector divided by the vector itself. So the C2, the norm of this C2 or C3, so C2 and C3, they're both going to be equals to lambda. And you do some simplification. So I'm not going to write all the technical details. So you can reorganize this whole thing in terms of lambda. Okay, so for the lambda squared term, you have twice the phi of e minus the real part of the phi of xy inverse. That's your lambda squared term. And for your lambda term, you have twice the phi x minus phi y absolute value. And then finally, you have the constant term, which is just phi of e. Okay, so this is going to be greater than or equal to 0. And just one thing, one little trick is that because phi of e is real already, so you can just pretend the real value is outside. So you say the real of phi e minus phi of xy inverse, all right? So because this inequality is always greater than or equal to 0, so this is for all lambda, so its discriminant has to be less than or equal to 0. So that's basic math. So what you have is that, okay, so you have A, this is B, and this is C. So B squared minus 4 times AC has to be less than or equal to 0. And you just expand it and you get the desired inequality, okay? So I'll just leave it here. It's way too technical. All right, anyways, so now we have this nice lemma, and of course the corollary is that phi is automatically uniform continuous. So I just want to write down a few definitions. So let's define the P of G. Okay, so that's basically all the positive definite functions, all the G to C where phi is a positive definite function. And of course, I already assume it's continuous. And we basically prove that they're actually living inside the L infinity of G. Okay, so they're inside there. And I also write P1 of G to be all the phi from, well, let's just write phi inside P of G with the norm actually equals to 1. Okay, so where phi, the uniform norm, because it's in L infinity, that's equals to 1. And we show the infinite norm is essentially just phi of e. So this essentially corresponds to all this phi where the phi e is equals to 1. Okay, so this is P1. And finally, let's just use the notation of P0 of G. Basically, it's the unit ball of the P of G. Okay, so everything, in other words, that's everything inside the P of G where the infinity norm is less than or equals to 1. Okay, this is essentially all the phi inside P of G. Where phi of e is between 0 and 1. Okay, we know phi of e has to be at least 0, but it's going to be less than or equal to 1.